The other power cycle types to consider are those types where the working fluid moves back and forth between the gas and liquid phases. And again, typically these types of power cycles are operated with external combustion, which should make some sense, because if the working fluid moves back and forth between the liquid and vapor phases, then probably the working fluid will be reused and recycled in the thermodynamic cycle and used as the working fluid again. And so in that case, you can't burn anything in the working fluid like you can with air, because that would change the properties of the working fluid and it wouldn't be able to continue. So typically these types of power cycles, these vapor power cycles, will involve external combustion. So that's what we will consider in this set. Now, if we're going to have a working fluid that moves back and forth between the vapor and liquid phases, or the gas and liquid phases, then we should probably draw a vapor dome, because the vapor dome helps us say something or understand something about the properties of the working fluid that are important, right? I mean, the specific volume of the working fluid is certainly something that we're interested in, because if we use a high specific volume fluid to expand and a low specific volume fluid that is compressed, we should get some net work out of the cycle. So if we need the vapor dome, let's just consider it. We've got a TS diagram here because, of course, we now realize that temperature is probably the most important variable, since it really is the thing that's closest to how much internal energy there is on the molecular scale without being the internal energy itself. So this TS diagram is what we'll use with the vapor dome. Now, we need to find some cycle that would adequately represent a real cycle. So what if we consider the Carnot cycle? Could there be such a thing as the Carnot vapor cycle? Well, let's think about it. On the TS diagram, the Carnot cycle is just a rectangle. So we could draw it and move it around wherever we want, assuming that we would operate our engine in that region. And so here's an example where we have state 1 to 2, the isothermal heat addition, above the vapor dome. State 3 to 4 is inside of the vapor dome for isothermal heat rejection, and then isentropic expansion on the right, isentropic compression on the left. And so considering this and trying to decide, if we actually have a power cycle like a steam power cycle, how well would each of these processes approximate the real process? And we can consider and think about it and use some logic and decide that really from 2 to 3, the isentropic expansion, well, notice that's over in the vapor region, right? So it's a gas. I keep saying vapor. I should say vapor usually refers to something that goes back and forth between the liquid and gas states or phases. But typically we reserve the word vapor for talking about that type of fluid, but when it's in the gas state. So I would rather just say gas to make it clear. So anyway, so isentropic expansion from 2 to 3 makes some sense. I mean, you can make a turbine, for example, that allows a compressed vapor to expand, or there I go again, a compressed gas to expand. And ideally you'd have a setup that is reversible and isentropic. So, no heat transfer, and it would have no friction, would have no uncontrolled expansion. So 2 to 3 is not that bad of an approximation for a real system. 3 to 4 looks really good because it's isothermal heat rejection. So if you think about state 3 being on the saturated vapor line and state 4 being on the saturated liquid line, well, at the same temperature, the saturated vapor is going to have more energy in it than the saturated liquid. So the idea that we could reject heat, in other words, decrease the amount of energy going from state 3 to state 4 by giving up heat, so heat rejection, and do that at constant temperature, well, that's actually very easy to accomplish in the vapor dome. Because under the vapor dome, the temperature and pressure depend on one another. So if we just hold the pressure constant from state 3 to state 4 as we allow heat to be lost from the working fluid, it'll naturally remain at a constant temperature. So this is nothing more than a heat exchanger, basically. So that's easy. So that process is looking good. So far, the Carnot cycle is looking like a really reasonable approximation. That's a good thing, because the Carnot cycle is the best that we could do, right? From 4 to 1, isentropic compression. Well, if we look at that region, it's more over in the liquid region, right? Of course, it does go above the critical point. So from 4 to 1, again, this would be compression, but going up to a higher pressure, essentially. The temperature would potentially rise. And what we would do here is use a pump, right? Because a pump can pump liquid to a higher pressure. So ideally, you'd want that pump to be isentropic, so reversible and adiabatic. So all of these look really good. The problem with the Carnot cycle as a model for the ideal vapor type of cycle is the 1 to 2 isothermal heat addition, because if we've got something that's above the critical point and we're adding thermal energy to it, getting the temperature to remain constant would be quite a trick. We'd have to change the pressure, control the pressure very precisely, and that would be very difficult to do. So the problem with using the Carnot cycle as the ideal vapor cycle is the process of isothermal heat addition. So it simply won't work. We can't maintain a constant temperature during heat addition, at least not very easily. So this is not an ideal model of a vapor cycle. Now, if you think about what happened, the process from state 3 to state 4 was wonderful, right? It was in the vapor dome before, and so the temperature was naturally held constant if we held pressure constant. And so that looks pretty good, and that gives us an idea for the process from state 1 to state 2. What if we take the whole Carnot cycle and just move it all down? So we're going to reduce the temperature of the cycle, which might decrease the efficiency a little bit, but of course if we keep the temperatures, the high and low temperatures, far enough apart, really it's the ratio of the two on an absolute scale that matters. So we could move the whole Carnot cycle under the vapor dome, and then the process from state 3 to state 4 would be, no problem. The process from state 1 to state 2 would also be no problem at that point, because now it's under the vapor dome. And so again, just holding the pressure constant while we add thermal energy, again, this can just be a heat exchanger, and it could work. It could be easy to do. So moving the Carnot cycle under the vapor dome to represent the ideal vapor power cycle so far is looking pretty good, because really there's two of these processes that now look like they would work. But what about the other two? Well, if we have an isentropic expansion device going from state 2 to state 3, notice at state 2 we begin with a saturated vapor. It's all a gas. But in state 3, there's a significant percentage of the working fluid that has become liquid. So if we're trying to use a turbine blades spin at high speeds, and if the working fluid is giving up energy and some of it is converting into liquid, then that means we're going to have drops of liquid impinging on these high-speed turbine blades. The turbine's simply not going to last very long. This is a very bad idea. We don't want to do that. So if we had an isentropic turbine, obviously that's a good thing, right? We'd want the turbine to be reversible and to, all the expansion of the gas to actually be transformed into work. So that would be ideal. However, the amount of liquid in the exit of the turbine just makes it impractical. We simply can't build a turbine that could withstand that sort of abuse. Imagine that you're, going through a rainstorm at 1,000 miles an hour with no windshield. Okay, that's kind of what we're talking about here, with these drops of liquid hitting the turbine blades. So we've got a problem here. 2 to 3 didn't work quite as well under the vapor dome as it did outside of the vapor dome. We have a similar problem in the process from state 4 to state 1, because we're going from a combination of liquid and gas up to state 1. Well, state 1 is going to be hard to hit with controls because we need to land on a state that is a saturated liquid state. But what kind of compressor is there out there that can compress both liquids and gases? I don't know of any. So, what we might have to do is separate off the liquid from the gas, use a pump on one side and then a compressor on the other, and it just seems like a mess, because after all, even if we do that, the compressor has to output something that is all liquid. So this doesn't sound like a very good strategy. So basically the two processes that say, the Carnot cycle is just not a very good model of the ideal vapor power cycle, it's really the expansion and compression in this particular case. The Rankine cycle takes the best of both worlds. Remember, we had the Carnot cycle above and outside of the vapor dome and then under the vapor dome. It was great under the vapor dome for the heat addition and rejection processes, but the expansion and compression processes work best outside of the vapor dome. So rather than using the Carnot cycle, we'll simply use what's called the ideal Rankine vapor cycle. And notice it does exactly that, right? The heat addition and the heat rejection processes, sort of the horizontal pieces of this process, from 2 to 3 is heat addition in the boiler, 4 to 1 heat rejection in the condenser. Those processes are kind of like they were under the vapor dome. Now, part obviously of the heat addition process from state 2 to state 3 does not occur at constant temperature. We're going to make it occur at constant pressure because essentially we're going to use a heat exchanger, which is a common piece of industrial equipment, in order to add heat and take the liquid coming out of the pump from a liquid all the way to where it boils off and becomes a superheated vapor at state 3. Notice that state 3 is in the superheated region, whereas state 2 is in the compressed liquid region. So we've got to go all the way from, compressed liquid, where we increase the temperature, a sensible energy change, to the point on the left of the vapor dome, saturated liquid, so that we boil it off into all saturated vapor, which is on the right side of the vapor dome at the saturated vapor line, and then continuing across or along that constant pressure line, continue to add thermal energy to the now saturated vapor so that it becomes a superheated vapor at state 3. And so that whole line from 2 all the way to 3 is a constant pressure line. And notice that under the vapor dome it is constant temperature because, since the pressure is already determined, that's the only degree of freedom we have under the vapor dome. So the temperature is already determined by the pressure that we set coming out of the pump. And then from state 3 to state 4, we might end up, that's going through the turbine, we might end up with a little bit of liquid coming out of the turbine, but as long as it's a very small amount, and we're not talking about drops, but little bitty atomized particles, maybe that'll be okay. And then from state 4 to state 1 is the condenser, where all we really need is a steam trap that prevents any steam from exiting the condenser. So the condenser then gives off a lot of heat as the vapor is transformed into liquid. And you can see Q out the waste heat there. From state 1 to state 2 is going through the pump, and now of course we can use a pump, which is very efficient, because if what we have at state 1 is a saturated liquid and the pump increases the pressure of that liquid isentropically, then state 2 will be directly above state 1. What that means is we'll remain in the liquid region. In fact, we'll end up in the compressed liquid region. So we can use a pump to do this. We don't need a compressor, and that's very good, because if the turbine is operating with steam, which has a very high specific volume, and the pump is operating with liquid, which has a very low specific volume, then the amount of work we get out of the turbine is going to dwarf the amount of work required to go into the pump. So you could easily have a turbine that generates a couple hundred megawatts and yet only require a pump that requires, maybe a couple hundred, maybe even 1,000 horsepower, which is nothing by comparison to, a turbine that generates a couple hundred megawatts. So this is the ideal Rankine cycle, and notice that there is constant heat rejection in the condenser, constant temperature rejection in the condenser of heat, but there is not constant temperature heat addition in the boiler. The temperature of the liquid as it goes through the boiler and becomes steam changes, not only as it goes from compressed liquid to saturated liquid, but also as it goes from saturated vapor to superheated vapor. So let's consider the math behind the ideal Rankine vapor cycle. Since each of the components, the boiler, the turbine, the condenser, and the pump, are open devices, we have to consider enthalpy, because now we have a flowing fluid going through each of these devices. So from 1 to 2 is isentropic compression in the pump, 2 to 3 is constant pressure heat addition in the boiler, 3 to 4 is isentropic, constant entropy expansion, and then 4 to 1 is constant pressure heat rejection in the condenser. So just going through them, there are some equations that are useful in each of these processes. One that is particularly useful is the amount of work required by the pump. Now, what the pump does is you put work into it and the fluid power changes, right? The amount of energy in the fluid, the liquid, as it flows through the pump, increases. So the enthalpy of that fluid in state 2 is greater than it is where it comes into the pump at state 1. However, that's not really what will be the most useful to us. The one fact that is useful, and wherever this is in your book, you'll definitely want to tab it, and you'll probably want to write some of these equations next to the TS diagram for the Rankine cycle. But one really important thing to keep track of is that point 1 is on the saturated liquid line, and that's really important because what that means is that the enthalpy in state 1 is exactly the enthalpy of saturated liquid at the condenser pressure. Notice from state 4 to state 1, the pressure at state 4 and state 1 is the same. This is just a condenser, it's just a heat exchanger. These are open pipes, so how do you pressurize the stuff on one end of the heat exchanger since it's an open pipe to the other end? The pressure is going to simply equilibrate. Obviously, since there's flow, actually there's going to be a little bit of pressure drop in the pipe, but don't worry about that right now. These are idealizations of the cycle. What's important is that the enthalpy at state 1, the entrance to the pump, will always be the enthalpy of saturated liquid at the entrance pressure to the pump, because that's, then the way we make this happen is that we use a steam trap on the condenser so that all steam is routed back into the condenser and only liquid comes out. And therefore, if only liquid comes out and it's all in equilibrium, well, then it's a saturated liquid. Now, another form of the pump work equation that will be more useful to us is this one. And this comes from considering an ideal pump. And what I mean by ideal is an isentropic pump, a pump that has no heat transfer and no irreversibilities. So another way to represent it besides H2 minus H1 is the specific volume of the liquid multiplied by the pressure change of that liquid across the pump going from state 1 to state 2. So there are two forms, notice, of the pump work, or the specific pump work that's required. One is the enthalpy change, the other one is V delta P, where V again is the specific volume. Now, what specific volume would you use? The specific volume at state 1 or at state 2? Well, since state 1 is on the saturated liquid line and we don't have compressed liquid tables, so we don't know the properties in state 2 really, what we would do is use the specific volume in state 1, because as the pump tries to compress the liquid's going to be pretty much incompressible. The pressure is going to go up, but the volume of the liquid will not change. In that case, the specific volume at state 1 and state 2 would be just the same. Now, obviously, there's going to be a little bit of a difference, but it's not enough to concern ourselves with. So the specific volume you would use in this equation, I probably should have put a subscript 1 on it. And how would you find it? Well, the same way you'd find the enthalpy in state 1. This, again, is a state at state 1 that is just saturated liquid. So V1 would be VF at P1. So there's the equation to remind you. So you should write these things down. Now, the enthalpy difference equation for the pump work is still useful, so you should copy it as well. What about the boiler? Well, constant pressure heat addition in the boiler sounds good, except that the temperature changes. Now, fortunately, that doesn't really matter, because if we know the enthalpy of the liquid in state 2 and we know the enthalpy of the superheated vapor in state 3, that's an enthalpy change, and we really don't have to worry about the fact that this boiled off. It's taken care of automatically by the enthalpy tracking all of the energy in the liquid and the vapor. Now, you're going to look up these properties in different areas. You look up the enthalpy in state 3 over in superheated tables, and the enthalpy in state 2 you would look up in compressed liquid tables if you have them. We'll go a different way because we don't. It'll be a good approximation. I'll show you that in a second. But both of those tables have to be based on the same reference state. Just like if I have two different items, I've got a calculator here and a little programmer I bought. If I want to compare the height of these two, I have to measure their height relative to the same reference, like the desk surface that I'm working at. I can't measure one relative to the floor and the other one relative to the desk surface, take the difference between those two heights and it mean anything, right? Because there's an offset between the two references. So in the same way, the enthalpies that you get for the for the superheated vapor and the compressed liquid in state 2, they have to be based on the same reference state where enthalpy would be defined as 0. But you don't have to worry about that too much because our tables in the back of our book already are. So that's fine. What about the enthalpy in state 2? What could we do with that? Well, I'll show you that in just a second, but I want to address it now. The enthalpy in state 2 is not something we can look up. Now, we know the pressure in state 2 because that would be a design parameter for this system, okay? Or maybe it's something we have to specify, but the point is that we can't get the pump work before we have the pressure in state 2, so most of the time that's going to be something that's given. If the pressure in state 2 is given, and we can calculate the pump work that goes into the pump, then we could use the pump work form that is enthalpy in state 2 minus enthalpy in state 1, because we already know the specific pump work in. And then the enthalpy in state 1 is just the enthalpy of saturated liquid at the condenser pressure. So H1 is known, the pump work is known, and so we would calculate H2 as the pump work plus H1. Now you'll see that in an example problem, but you might want to rearrange the equation that you see there sort of ghosted out and just write H2 equals H1 plus the pump work, because that's the form of the equation that would be really useful, and it's really useful when we're dealing with the energy balance on the boiler, because that's where we really need H2. Okay. The turbine specific work output is proportional to the enthalpy change of the steam across the turbine, so that's pretty straightforward. And then the heat loss, the specific heat loss, is again just the enthalpy change across the condenser, H4 minus H1. So here are all the equations that we would need in order to deal with this cycle. Now again, you should write all these equations down or highlight them on the very same page where the Rankine cycle is shown in your book, and of course don't forget you need a tab in that page. So what can we learn from this? Remember, with all of our gas cycles, what we did is we took 1 minus Q out over Q in. Can we do something like this? Well, not really. The thermal efficiency is still 1 minus Q out over Q in, but most of the time we don't go that way. We don't take the two energy balance equations for Q in and Q out, plug them in, and do a bunch of simplification and find something that's particularly useful. Rather, the way that this is usually quantified in industry is by something called the heat rate. Now, this cycle we're talking about is probably the whole reason you're able to watch this lecture with electricity, because in this area of the country, the Ohio Valley region, a lot of our electricity is produced from the Rankine cycle, burning coal, burning natural gas. Now there are a couple of cycles, of course. There are gas power cycles that are an air cycle, but a lot of the modern combined cycles use gas power cycles, and the waste heat from them still drive a steam turbine. And that makes the system more efficient. But anyway, heat rate is something that you would talk about typically at a power plant. It makes some sense. It says, how many BTUs of heat do you have to put in versus kilowatt hours produced? Because if you think about the power plant, what are they doing? I mean, a plant is something that produces something, right? Well, they're producing electricity. What from? Well, from a fuel, right? So they're taking a fuel in, and their product that they produce, their production, is electricity. So they talk about electricity production just like a manufacturer will talk about, say, production of cars, right? That's what they do. They take in raw materials, produce a car. Well, power plants take in energy, typically in a chemical or sometimes even in a nuclear form, convert it into then electricity. So really, if you think about it, what do you want to do? Do you want to, let's just talk about your car for a minute. Do you want to put 100 gallons into your car to go 10 miles, or would you rather put a gallon in to go 10 miles? Well, obviously you'd rather put in a gallon and go 10 miles. In fact, that's still pretty crappy fuel economy. You'd like to put a gallon in and go 100 miles, right? So when you look at that ratio, what you're doing is comparing, what you have to put in versus what that you get out of it. And so while efficiency is desired output over required input, the heat rate is kind of the inverse of it. So it's how much energy is required in the form of thermal energy to produce a kilowatt hour of electricity. And the lower the heat rate, the better. Just like the lower the gallons per mile in your car, the better. Okay, that's the same sort of thing. So if you think about your fuel economy of your car as gallons per mile, you understand better what is meant by a heat rate. It's energy in the form of thermal energy per mile. Now, there is a relationship between thermal efficiency, which has no units, and heat rate, which has units of BTUs per kilowatt hour. And there's a conversion factor between the two naturally. So you see it here. The thermal efficiency is 3412 BTUs per kilowatt hour divided by the heat rate, which is in BTUs per kilowatt hour. And so the thermal efficiency, again, ends up being dimensionless. Now, if we don't have some clear direction, what could we decide to do? How would we proceed? What would be our goals in order to increase or maximize the efficiency of the Rankine cycle? Well, if we look at what's going on, we can understand it. Our thermal efficiency equation still applies, and we can look even farther back to the Carnot cycle for some inspiration. If the cycle is reversible, which understand the Rankine cycle is based very closely almost on the Carnot cycle, right? I mean, it's pretty close. The only difference really on the TS diagram is that the upper bar going across, the heat addition portion, is just not at constant temperature like it is with the Carnot cycle. But with the Carnot cycle, one of the things that we learned was that the thermal efficiency would be increased by either raising the temperature of the source or decreasing the temperature of the sink. So in the case of our Rankine cycle, if we were to decrease the condenser pressure, well, we only have one variable under the vapor dome, so that would decrease the temperature at which we're throwing away waste heat. So we're throwing away heat that is, or thermal energy, that is less useful, that is at a lower temperature. And that should increase the efficiency of the cycle. So if you look at the TS diagram for the Rankine cycle, you notice that what happens when we go from 1, 2, 3, 4 to 1 prime, 2 prime, 3, 4 prime, when we change our cycle by reducing the condenser pressure, well, there's a net amount of work that is added. There's an increase in the work output, and yeah, there's an increase in the heat rejection and the heat addition, but it turns out that that increase in work output offsets it. We do end up with a more efficient cycle. Now, we need a pump that can produce, you know, a higher pressure difference from state 1 prime to state 2 prime rather than from state 1 to state 2, but this figure is not very accurate because that left line with 2 prime M2 shouldn't be so far away. It almost lies on top of the saturated liquid line, so that's really not a big concern. Now, where problems arise, well, let me continue. So if we decrease the low temperature at which heat is rejected, the problem is we'll increase the liquid in the turbine output. So 4 prime has a higher percentage of liquid coming out of the turbine than 4. And that's one of the things that limits this approach of decreasing the condenser pressure. The other thing that happens is that these cycles typically operate with water. Now, not water like you get from the tap, but water that not only is very pure and doesn't have as many, you know, dissolved solids and things in it, like, you know, calcium and so forth, but also this is water that typically has the oxygen removed, because the devices, the boiler, the condenser, the pump, the turbine, these things are often made with a lot of steel, and so if you add water to steel and oxygen, you will get rust, and we can't afford that, right? You don't build a, you know, billion-dollar plant and then it rust away in the next week. That's not that's not reasonable, right? In fact, these plants should be made to operate, you know, with significantly long lifetimes, at least 50 years, sometimes 100 years. So anyway, the liquid, the working fluid that's cycling through and going through all the different pieces of equipment is very valuable. You wouldn't just throw it away. That would be a bad thing. Now, there are reasons why at times you might have to lose some of it, but you really don't want to. If we decrease the condenser pressure, what can happen is that we could end up with a condenser pressure that is below atmospheric. If that happens and somehow a leak is developed in the system, especially around the condenser, then air will leak into the system. But we wouldn't detect it because the direction of flow would be from where we're at to inside of the process. And as this is running constantly, we would never see the leak. And so what would happen is we would end up with oxygen in that very expensive liquid. And what would happen is exactly what we don't want to happen, right? All of this system would just rust. We wouldn't know about it potentially unless there's some way to sense it. And we'd have scrap metal on our hands instead of a power plant. So there's a limit to how low the condenser pressure can go because of the danger of oxygen working its way into this liquid. Now, while this liquid is valuable, the process itself and all the devices are more valuable. So if we develop a leak, what we'd like to have happen is have the liquid leak out. We'd like to see the water leaking out so that we can detect it, correct the problem, and continue and not destroy our equipment. So pressures below atmospheric are simply not wise in most cases unless you have a really good way of making sure that there are no leaks of air into the system. So that's another thing that limits this approach of reducing condenser pressure in order to increase efficiency and decrease what's called the heat rate. What else could we do? Well, again, let's turn to the Carnot cycle, and it suggests that if you could raise the temperature at which heat is added, well, then that would be a good thing. So if we were to increase the temperature of the steam going into the boiler from 3 to 3 prime, well, then look what happens. We generate more work. Of course, we have to put more heat in, but it turns out to be more efficient. The reason it's more efficient is because, look, we're adding heat to the cycle from state 2 up to the saturated liquid line, and then from the saturated liquid line all the way across to the saturated vapor line, then from the saturated vapor line up to either state 3 or state 3 prime. Now, if you think about the average temperature at which we add heat from state 2 to either state 3 or state 2 to state 3 prime, if we go all the way to state 3 prime, that's an average higher temperature at which heat is introduced into the cycle. So while there's not just one TH to consider, if we could increase the average temperature, then we should be able to increase the efficiency of the cycle overall, taking a cue from the Rankine cycle or any reversible cycle. And sure enough, we see that there's an increase in work, even though, of course, there's an increase in heat addition. And so it turns out that this would increase the cycle efficiency. So, and the reason it does that is because the increase in the high temperature at which heat is added. Now, there's a side benefit from this. Notice we've gone from state 4 at the exit of the turbine to state 4 prime at the exit of the turbine. Notice that 4 prime is closer to the saturated vapor line, and so that represents a decrease in the amount of liquid in the outlet of the turbine. So this is a good thing, right? This is overall a very positive thing. No problems yet. The problem that you run into very quickly, though, is that steam can cause turbine blades to creep. If the steam is at a high enough temperature, I mean, if it's super high, it could melt the turbine, unless you have exotic materials that the turbine blades are made from. But there's a maximum temperature, no matter what material you use, that the turbine blades can accept. And that maximum temperature for regular steel type metals is about 1150 degrees Fahrenheit. Above that, the material softens, the blades weaken and can creep, because remember, this turbine is still turning extremely fast. 100,000 RPM is not unreasonable, and so this the forces required to hold those blades onto the rotating shaft is immense. And so if you soften the metal by going up to too high a temperature, then the blades will, the materials made from will eventually fail. So there is a maximum, there's a limit to this based on materials of the turbine. Now, you notice that we really weren't attacking the right part of the curve, right? We were over in the high temperature region. Why, if there's a limit, we can't really increase the average high temperature at which we add heat. The real problem's on the left-hand side, right? The real problem is at state 2. That's the lowest temperature at which heat is transferred into the system. If we could increase the boiler pressure, well, then state 2 prime would be above state 2. It would be at a higher temperature effectively. And so this is a better way to increase the average temperature at which heat is added, because we're attacking the problem child, if you will, right? The area where heat is added at the lowest temperature. Now, notice that by increasing the boiler pressure, when there's a maximum temperature we can introduce into the turbine, we do have to sacrifice a little bit, right? The turbine has to move from 3-4 to 3'4 prime, and so there's an increase in average or in the net work output of the cycle, but there's also a roughly equal decrease in net work output by moving the turbine from 3'4 to 3'4 prime. But this is still more efficient because we're adding thermal energy to the cycle at an average higher temperature. Now, that's a good thing. We do produce more energy per BTU of chemical energy used, or of heat added. But we've got the problem we've ran into several times, where 4 moves to 4 prime. That means an average higher percentage of liquid in the output of the turbine. So that's the problem. So while we increase the average temperature at which heat is added, we also increase the liquid output of the turbine, which is a problem. Now, the other thing that happens is, since we have an increase in boiler pressure, well, we're going to require more metal so the boiler doesn't just explode, right? It's got to be a stronger pressure vessel. The turbine has to be a stronger machine, right? It again has to experience very high pressures, and the pump has to experience high pressure. So that's more metal that we have to throw at it. And essentially it's a larger system for basically the same power. Now the advantage is that we increase the efficiency of the system within reason. You know, we can't obviously decrease the quality of the fluid coming out of the turbine too much. But this is not so bad. I mean, if this was a mobile system, it might be a problem, but the increased weight is not really a big deal if it's just a power plant that's going to sit on the ground somewhere. And material is fairly cheap, so this is not a real big problem. The main problem here is the extra liquid coming out of the turbine. Now, if we want to use exotic materials, metals that can take much higher temperatures, we could really increase the boiler pressure more and operate with what's called a supercritical power plant. A supercritical power plant operates above the critical point of the working fluid, and you know that's going to be water, unless you're talking about some research cycle. So operating above the critical point of water means that the pump is really pressurizing the water, and then the boiler just basically flies above the critical point to state 3. Now, obviously this is much higher temperature than 1150 degrees Fahrenheit, so you have to use expensive exotic metals so that the turbine doesn't melt down and doesn't fail. It can be done, and so there are what's called supercritical plants. They are more expensive to build, they're more expensive to maintain because everything is, you know, real high pressure, exotic materials, and so they have to be operated well. But it's kind of like saying I could buy a car that's really expensive but gets 100 miles per gallon, you know. So there's a lot of trade-offs here to be considered. Because of safety concerns, nuclear plants are not operated supercritical as far as I know. I've not heard of one that is operated supercritical because you've already got the complication of the nuclear energy there and the fusion process that's occurring. I'm sorry, fission process that's occurring. You're splitting, not adding together. If it was fusion, I think we'd be far in the future. But anyway, so it's kind of interesting. Most people don't know, but nuclear plants actually don't operate at as high a thermal efficiency as a lot of coal-fired plants do. So that doesn't mean nuclear is a bad choice. Just like, you know, just because one person drives a Prius and you might drive a, I don't know, let's say a pickup truck, that doesn't mean that your choice was wrong. I mean, think about it this way. If what you're trying to accomplish is moving a pallet of roofing material, number one, the Prius probably can't hold that load at one time. The truck can, so you make one trip with the truck. Maybe you have to make 10 trips with the Prius. Well, that's not going, I don't care if you are getting 60 miles per gallon, that's not going to beat out a pickup truck at 15 miles per gallon, right, if you have to make 10 trips. So having the right engineering solution for the right problem is important, and there's enough variety in the market, and you know what percentage are industrial customers, how much the load fluctuates based on the region of the country, that you know nuclear plants might be practical somewhere, they might be impractical elsewhere. I'm not the kind of person that says there's just one solution that works for everything. I don't think that's true. I think you have to take into account the diversity of the region to select the type of plant that is beneficial. Now, you may not know this, but since utilities are essentially monopolies in most areas, they are heavily regulated. And so what you'll find is that utilities often cannot just choose to install any type of machinery they like to produce electricity from a fuel. Obviously, nuclear is one of those that's very much resisted. I do have concerns about nuclear power. However, I also see the extreme benefits of it. But all that aside, companies are often very regulated into ways that they're allowed to upgrade or rebuild power plants, and most of the time they're simply required to choose the solution that passes the lowest costs on to the customer. You can argue about whether that's beneficial or hurtful in the long run. I think there is something to be said for regulation when there's, you know, a large monopoly and there's not really a better way to do it. So I guess I just always want to concentrate on the engineering side and try to make nature serve us the best we can, you know, and hope that the politics and everything else will be worked out. Another thing that I think is really important is I want people to learn about energy and its production. People use energy like crazy. I mean, I don't think there's anything we human beings use as much as energy and yet are so ignorant about it on average in the population. I think that's very sad. I think that's a tragedy, really, because then how do people make intelligent choices about their own energy usage, or they're voting for policies around energy usage? I don't see how you do that. I think that our school system needs a whole lot more curriculum devoted to energy, because it is fundamental to our modern way of life. But that's my soapbox and not engineering. So let's move on. So of course, what's the advantage of increasing the boiler pressure to supercritical pressures is the overall average increase of TH, the temperature at which thermal energy is added, and so you get a benefit in efficiency because of it. Now obviously these involve very high pressures, and so you got to throw a lot of expensive metal at it, but it can be done. The other thing that really limits this is the increased liquid in the turbine. Even if you have an exotic metal, it still only has so much strength, and pitting it is possible with liquid droplets, impacting on the surface at very high velocities. I would ask you to read the text on pages 326 and 327 to learn more about nuclear power plants and supercritical cycles and so forth.